This is my opening slide. A walk in the Lindenmayer fractal forest with a Kotlin notebook. I'm Maia Grotepass. This is not going to be a slide presentation. This is going to be a demo. For you that are perceptive, might notice that I'm no longer in the slide presentation software. I am now in IntelliJ IDEA, and I'm in a Kotlin notebook. So welcome to my talk, A Walk in the Forest with a Notebook, or A Walk in the Lindenmayer Forest with a Kotlin notebook. Who am I? I'm Maia Grotepass. I'm an Android engineer by day. I'm working at Conto. Shout out to my Conto besties in the front row there. But for this talk, I'm not an Android engineer. I am what I like to call a shiny tech magpie. So why this talk? A year ago, I saw an announcement about Kotlin Notebooks. I am not a data scientist. I know nothing about Kotlin Notebooks, but I am attracted to shiny new tech. And so I collect experiences in shiny new tech, and I thought, let me try out a Kotlin Notebook. And so this talk is my experiences, and I'm going to take you through the path that I followed, just exploring Kotlin Notebooks. And the topic we're going to use is Lindenmayer systems, or Lsystems. Why Lsystems? Just because I find them interesting and because they're a good piece of code to use as an exploratory mechanism in code. If you need to find me on the internet, my handle is Maia Today. If you just search for Maia Today, you will find me. Okay, so a little bit about, where's my cursor? A little bit about notebooks. So this is an image. It looks like a slide. What's happening here? So in a notebook, for people who don't know notebooks, you can have Markdown, which is over here, you can see. You can have a cell with Markdown, or you can have code. So I'm scrolling up, and you can see, what am I doing? I'm just pulling in some Java code. I've got a little function here that reads a file from disk. I'm reading a file from disk. Why? Because conference Wi-Fi is really weird. I could have used an HTML URL, but I'm reading a file from disk. This image show, it will output a buffered image. This is a Java buffered image. The cool thing about Kotlin Notebooks are that if you have a cell like this, if there's an output that the notebook understands, be it text or be it a buffered image, it will display it for you. So here I'm calling show me this JPEG, and I'm getting this JPEG. Okay, now, what's the definition of a road, and what's the definition of a path? Now, a road is when you connect from A to B, and the sole purposes of a road is to connect A to B. A path is highlighting the space that you pass through. So this talk is going to be more like a path and less like a road, because it's a walk after all. And now, because it's a walk and because it's a path, we're going to take our first detour. So the question I had was, I love paper notebooks. Paper notebooks allow me to draw things. Paper notebooks allow me to write things, but I can't run any code in a paper notebook. In a Kotlin notebook, I can write things, I can have images, I can run code, but can I draw? Good question. Now, I know we've got a buffered image, so I'm going to go into a detour here, and we're going to have a look. So what if I could, in a Kotlin notebook, just say, I want a canvas, let's draw on this canvas. But I've only got a buffered image, which is a Java construct. So I wrote a little piece of code, which looks like this. It's a function. I'm saying it's called canvas. It's got some setup things that you can set up. And the most important thing here is this piece here. It takes in a block, lambda with receiver, graphics 2D, and then inside this function, it does all the Java things that it wants to do to set up the buffered image. You don't need to worry about that, but the important piece is here. Once I've got this graphics 2D, I can call this block. And this allows me to do something like this. I can call the function canvas, and anything inside these brackets, I can draw on that buffered image, and I can draw on the canvas. Now, here's the cool thing about a notebook. I can go Control-Enter, and it will draw. So you can see here, I drew 200 of these ovals. I've got some helper functions to do random colors, random radiuses, random offsets. To see if this is live, let's make it 100. Or let's make it 150. That's not going to work. Ooh, let's try that. So you can see, so I know now I can draw, I can write, and I can write code. So let's go back to the forest walk. So the first people that we meet in our forest is a person called Benoit Mandelbrot. I am not a mathematician, but Benoit Mandelbrot was a mathematician. But more importantly, he called himself a fractalist. And the reason for this is there were geometric constructs which people called monsters before, but he coined the term fractal. And if I were to ask you what is a fractal, you'll get different kinds of varying answers. But let's look at what a fractal is for the purposes of this talk. So the first thing you see with a fractal, I think the bigger image is over here. The first thing you see, this is a very famous fractal picture. This is called the Mandelbrot set. And the inside of the Mandelbrot set is the actual Mandelbrot set. So if a point on this canvas belongs to the Mandelbrot set, then it's drawn in black. If it doesn't belong to the Mandelbrot set, then it's drawn in another color. The interesting thing about this Mandelbrot set, if you take this image and you zoom into about there, you'll see this image, like that, with some details. I'm sure anybody who knows fractals and have been on the internet must have seen this kind of image as well. Now, and then if you zoom in again, so for instance, you zoom in at this little point over here, you'll see something over here that looks like that. And this is called self-similarity. It's not identical, but it looks similar. And the other thing that's interesting, if you think about the geometric construct of a triangle, if you zoom in on the edge, it becomes a line. But these mathematical constructs have got the interesting function that if you zoom in on the detail on the edge, it just becomes more detailed the more you zoom in. And that is the quality of self-similarity. The other thing about fractals are, they're usually quite simple to construct. They have a really simple formula to construct them. And they often use self-reference or recursion to get them. So I'm going to show you here. If you are a mathematician and you want to use a fractal notebook, what you can do is you can import later, and you can have the formula after it runs for a bit. So this is the simple formula of the Mandelbrot set. What it does is it starts with a coordinate and a constant, it squares it, and then it gets the answer, and then it feeds the answer back in. And if the numbers that come out go to infinity, then it's outside the Mandelbrot set, and if they stay bounded, then it's inside the Mandelbrot set. The other thing that a Mandelbrot set has is this surface, well, a fractal has, is this surface complexity or dimension, which is this idea. And in a strange, poetic way, it reminds me of the idea of a path and a road, where a road is just a connection between 2 points. And a path, on the other hand, goes into the space and highlights the space. And often the surface complexity, or the dimension of the fractal, sometimes creates what they call space-filling curves. Okay. The next person we're meeting in my forest is a man called Aristide Lindenmayer. And he wasn't a mathematician, nor was he a data scientist, but he was a botanist. And he was interested in understanding how plants grow. He wanted to find out an algorithmic way to describe how plants grow. So he figured out a language, and it is recursive as well. And I'm going to illustrate his algorithm for you using emoji. If you're wondering how I get the code so quickly, these are live templates in IntelliJ. So I created this plant construct. We'll go into the code of plant in a minute. But basically what you have is, you have some other kind of seed, also called an axiom. You have a starting character. And then you have a set of rules. And for every iteration, you apply these rules to your starting character, and then you get the output. I'm calling it a blueprint for the plant, but you get the output. So if I change this to be 1, and I run this, you should see that it got the stone and it replaced the stone with a stone and a plant. If I now change this to 2 and not make it crash, you should see the next replacement happening. But none of these rules have been triggered because it hasn't got that character sequence yet. And if I now make this 15, you can see the string becomes quite complicated and can be quite complex. And it's this recursion, this idea of recursion, or that you reapplying the rules to the output of the previous run that makes this complexity. But we're not seeing how the plants are drawn. And I'm pretty sure Lindenmayer didn't use emoji. In fact, he had like a dictionary, or there's a dictionary of commands that these plant algorithms use to represent different kinds of things. And at this point, I want to introduce our first creature in the forest. Now, I don't know if anybody knows Logo. It's something that comes out of the 60s. What they had was a mechanical turtle with a pen inside. And you could give it commands. You could give it commands to put the pen down, and then you could give it commands to move forward or to turn, and that way you could draw things. Now, the Lindenmayer systems, the letters, instead of emoji, they're using commands that this turtle, this mechanical turtle, could understand. Now, turtles live in the water, for me, and terrapins live in a river, and we're in a forest, so I called my algorithm tortoise, or in fact, it's a function called goTortoise. So what I'm going to do is I give the tortoise this plant, the plant blueprint that we got from the recursion, and then the tortoise will take that plant blueprint and draw on the canvas. Here are the commands that this tortoise understands. If it's a capital F, it will put the pen down and draw the line, move forward. If it's a small f, it can just move forward and not draw a line. If it's a plus or a minus, it can rotate in one or the other way. Now, here's an interesting one. If it's an open square bracket, it will just remember where it was. So what does it remember? It remembers maybe the x and the y position, some other parameters like length of the step it needs to take or the colors. And if at any time in the sequence you use the closing brackets, it will jump back to the spot where it was the last time that it remembered, like a stack construct. Now, if we feed this tortoise this plant, we say F, which makes it move one forward, then turn, move, turn, move, turn, move. The angle is 90. We should get a square, and then we have a rule to apply. So let's look at what this code looks like. Okay. So here we have the plant. I said I was going to jump into the plant and have a look at the code. We can do that now, and we can see what it is. There's a data class plant that knows about the starting string, that knows the rules, and it knows the output. It knows the iterations. It doesn't really need all of this information, but this is what the data class looks like. And then I've got a plant builder class. So this is immutable, and the plant builder class is mutable. It's the classic builder pattern. It's got this grow function, which will do the iterations. And you can see the thing that it does within the iterations, it just repeats for the number of iterations. And it applies the rule to the blueprint. And it just replaces whatever the key of the rule set is with the value of the rule set. And then the interesting part of the plant is this function, which is the plant function, which I call. And it will take a block, which we had, which describes the plant, and it will apply that to the plant builder, and then just build the plant from that. Okay, so we've got this plant that we've constructed, and now here's our goTortoise algorithm. So if I just go in there, we can look at what the tortoise looks like. So this is a repeat of the tortoise commands. And then this is where the tortoise lives. It has a state because it has to remember where it was before, and it needs to be able to jump back to the state. And you can see it's an X and a Y position, the length of its step, the angle that it's busy turning, a color index, and a stroke width. And then the actual goTortoise function is an extension function on graphics 2D. Why? Because I want to call it inside that block on the canvas, because I want this tortoise to be able to draw on the canvas in the canvas function that I just created before. And so let's look at inside the tortoise, how does it do it? It has a stack because it has to remember things. It's got some start state, which is like me taking this mechanical tortoise and putting it down on the paper and making it point in a certain direction. And for my purposes, it's pointing up. And then it takes this blueprint, this string that I got from the plant, and it iteratively goes through each of the characters and executes what it sees. If it sees an F, capital F, small f, It figures out, depending on its step, what its new XY position is. If it's a capital F, it will draw a line. So here's our side effect here. That's where the line gets drawn. And then it makes a new state and it returns the state out of the when. If it's a plus, this one I don't even need to go in. You can just see it changing the angle. It changes the state and it just changes the angle. Here's my opening bracket. It just takes the current state, adds it to the queue, and returns the state again. And if it's a closing bracket, it just pops the last state from that queue and returns it out. And so this is the turtle graphics of the tortoise algorithm that can draw on a canvas. So let's jump back here. Okay. Now, I'm going to comment this out. And we are going to just see it draw the square, which is the seed of this plant. So here, and if everything works, you should see a tiny square, which is what I'm expecting, yes. Okay, my zoom works. So there's my tiny square. Now, how the plant works, each of those edges of the square are going to be replaced by a little pattern. And so here's our rule. I'm taking the other side of the rule. I'm pasting it in there. We're running that. And so you can see here, that's what each of the squares will be replaced by. Okay? And now, if we comment that out again, and we comment back the blueprint, and we run it again. So this is a classic Koch curve. If people know anything about fractals, that's our classic Koch curve. The interesting thing for me here is the Lindenmayer systems themselves aren't fractals. It's just an algorithm with which you can generate a fractal, and if you use the right commands, you can give it to the tortoise, and then the tortoise can draw it. Okay. Let's look at some other examples. Now, if you look on the wiki, and you look up Lindenmayer systems on the Wikipedia, you get this plant. It has a rule like this with an X in it. The tortoise is going to ignore the X. It's not going to draw anything for the X. But the useful thing about the X is you can use it to, again, replace this piece. So you can use it as a placeholder inside in the way the plant grows and replace other pieces of strings in the places where the X are. And then it's just a question, again, of giving it to the tortoise, giving it an angle and making it draw. And this is what comes out if you draw that weed from that algorithm. Now, the tortoise is very deterministic. It always does the same thing. It never deviates. It's extremely reliable. If I run this again and again, I get the same answer. Now, that doesn't look like a forest. That doesn't look like a tree or a plant. There's no variation. So how can we add variation to this? There's two places I can add variation. I can either add variation when I generate that plant structure, or I can add variation when I'm drawing it. So let's look at the first step, which could be if I'm generating the plant. So here I've got 3 clones. I've got 2 plants. They use the same rules. The first one is just repeating the iterations. The second one, I have another method called sprout. And what I'm doing here is I'm giving it a probability. I'm saying, not all of your rules always apply. What you need to do is you need to roll a dice, and it's a 10-sided dice, and if the number is 9 or lower, then you apply the rule, but if the number is 10, or if it's a 9-sided, 10-sided dice, 0. Anyway, if it's 1 out of 10 times, it's not going to apply the rule. And then I've got the tortoise, and I'm letting the tortoise draw these 3 plants. One of them's green, the others are black, and they have different angles. So I can change the angle that the tortoise turns its head when it moves, but I can also apply this probability to the. So now I don't know if the green plant is going to look like the others. Yes, it's as big as the others, but if I run this again and again, maybe 1 out of 10 times, one of the rules it didn't apply, and because of that, it's like a shrunken plant because it's smaller, because it didn't apply all of the rules in the plant algorithm. But there's another way that you can get some variety in this algorithm. Now, I don't know who of you have watched a squirrel move. Now, squirrels, they run up a tree, and then it looks like they don't know where they're going, and then they pick a random direction, and then they just change direction, and then they run further. What they do is they hide behind the tree because they don't like me watching them, but they've got this idea, they've got a concept of that they're changing the angle that they're moving into. Now, there's a term called stochasticism or stochastic, and it means involving a random variable. So I took the tortoise algorithm, and I modified it to be a squirrel. And what the squirrel does is, it doesn't always change in the same angle. It changes its angles, and it picks different angles. So we can take the exact same plant, and we can give it to the squirrel algorithm and see how it draws it. The other thing I did when I added this squirrel algorithm is I changed it so that it draws the trunks. Some of them it'll draw thicker, and some of them it'll draw thinner. And I made it change colors so I can get some color variation. So let's see what that same plant in the previous example looks like if I let the squirrel draw it. So you can see the plant is exactly the same. I'm not even using the probability on the grow. I'm just asking the squirrel to draw it instead of the tortoise. So let's run that. And you can see the plant is already looking like the wind maybe blew it. And if I run this again a few times, you'll see I get different plants coming out of it. And this is just because the squirrel is changing its direction or changing the angle. It's also got a dice inside its little squirrel head, and it's changing the angle based on a random number. Okay. So we've got a shrub now. Now we need some trees. Now, if you look on the internet, there are quite a few of these Lsystem algorithms that you can use and that you can explore. And you can also fiddle and tinker with them yourself and see what the trees are. The one that I liked for this talk is this one. It looks a little bit like a Christmas tree, or it looks like a spring tree just before the leaves come out. And I'll show you it looks like that. This one is using the sprout method, which is using the probabilities on the rules, which means that it'll not always come out the same way. So if I run this a few times, you'll see I get slightly different trees. Some of them are taller, and some of them have slightly different angles between their branches. I'm hoping to get the little fat one. So there's the little fat tree. Okay. We have a tree. We have a shrub. But now I want to collect these trees. I want to put all of these trees together. I want to have multiple trees, and I want to have multiple shrubs. I want to have like seedlings in a forest. And so what I did for that is I had a look at data frames, and I created another notebook, which I'll show you here. It's a nursery notebook where I collect and make these different plants. So here I'm storing this function in this function called a tree builder. The reason why it needs to be a parameter, a tree builder parameter, the reason why it needs to be a tree builder parameter is because some of the variability comes in when in the generation phase of the tree, not in the drawing phase. So I have a tree builder and I have a shrub builder, and then I have a list, and then I just make 90 trees and 20 shrubs and put them in a list. And now here, I'm taking this list, I'm converting it to a data frame. Why am I doing this? Well, I wanted to play with data frames, of course, but also because a data frame allows me to add, to augment the data set. So I might get those plants, those data objects or data classes in the data frame, but I want to add some more things to it. And also, I don't want us to wait while I'm planting all these seedlings. I want to save it as a CSV. And that's a useful thing about data frames, is you can quite easily convert things that you have in code into a CSV, save it in a CSV, and read it back out. What I did here as well is I thought to myself, well, these seedlings, some of them are going to be in the foreground, some of them might be in the middle ground, some of them might be in the background. So here I randomly applied whether they're going to be in the foreground or the background. And here you can see what that data frame might look like. It's got the information about the plant. I'm not so sure why I can't make it scroll across. But it's also got a flag which says if it's a tree or a shrub, and it's also got this idea if it's in the foreground or the background. Now let's go back to my forest. And and we can see how we use this. So there's a bunch of seedlings in a CSV file in this repository. This is how I read it out. I pull in data frame. That's the easy way. You just go % data frame. And what this will do is it'll find the right data frame outside on the network, on the library resources. The same way Gradle does your dependencies. Pull in the dependency and pull in some of the imports that it needs. And then it's as easy as saying data frame, read this CSV. And then this plant's variable now contains the data frame of everything we generated from the nursery. If you look here, it takes a little while to run, but there you can see it's the exact same information that we saw in the other notebook, which is in the. Now, this isn't enough information for me yet. I now know that some of these shrubs or some of these trees are in the foreground or the middle ground, but I haven't placed them on the scene yet. And my tortoise has got this capability of knowing, you can give it an XY position where it starts drawing. So I want to be able to tell my tortoise where it should draw these trees. And also, I don't want all of these trees to be the same color and all of these shrubs to be the same color. So I actually want to take this data frame and I want to add even more information onto it. So now, let's modify this data frame then. So I made myself some helper functions. What this does is it picks a number between the width of the screen for the X position and between the height of the screen and ranges for the Y position. It's got a helper function to add colors. But the piece that's interesting here is this plants, that's the data frame. And here I'm adding columns to the data frame. I'm saying I need an X and a Y position. I want to add some colors. It might be random. Depending on if it's a tree or a shrub, it might be a different color. I want some different lengths of the stems, must be different lengths. And I want different thicknesses of the trunks and different angles like that. And so, if I run this, you should see now I have another data frame which has got the original. Oh, there's another step I forgot out, is that for drawing, I don't need the seed or the rules or the iterations from the plant. Those are extra columns that I don't need. So I can add new columns, remove some columns, and now I've constructed a whole data set of these trees in this forest. But I think we can't see them yet. So what's left to do now is to draw them. So what are we going to do? We're going to take a canvas and we're going to feed the data to the squirrel. So we have a canvas. This sky earth will just give me some background gradient, and we're going to filter and feed it to the squirrel. So if I run this now, you should start seeing. So here, this is the background trees, right? And we've got some faint trees growing in the background here now. If I now run the next line, we should see some middle ground trees appearing out of the mists. This is like springtime, but still cold, and there's some wind and clouds, but the trees haven't started budding yet, but there are some green shoots. We've got some foreground trees coming in the foreground. And lastly, we have our shrubs. Oops. We've got our shrubs growing in the foreground. That's not all, though. So the Kotlin Notebooks have got this interesting thing. I can generate this. So what I'm doing here is I'm making an ID. I'm picking an ID, just a string. And instead of outputting the image as a buffered image like that, what I'm going to do is I'm going to display it explicitly and tell it it's this ID. This is the ID of the image, of this buffered image that I want to display. So if I run this, it should look the same. We're expecting it to look the same, except for where the squirrel drew things differently. But more or less the trees are the same and their X and Y positions are the same. But I've got an ID for this image now. And now what I can do is this. I can pull in any other library, Kotlin library, that I know about, The coroutines you could have pulled in with the percent use coroutines. That would have pulled in the latest one. But I wanted to show you the syntax of this. You can pull any Maven coordinate of any library that's Kotlin that you like and know and can understand, and set its versions if you want like that. And so here I'm using it, and I'm just going run blocking. I'm repeating 100 times with a delay. I'm taking a canvas, but I'm giving this canvas the original image that I have. So my canvas function can take in an image and can draw on that image again. And then this is just going to draw some random colors and things. You'll see now what it draws. And then the crux of it is, here's this update display. So what I'm doing is I'm saying, don't give me a new picture. Take the picture from this coordinate here, from this string here, the one with that ID, and draw into that. So let's just run this, and what you should see. So these are the petals of the new buds that came out after spring that are busy floating around in the forest in the wind. Now, this is a walk, right? So we're on a walk, we walk through the forest, and this is our contemplation point where we can look back and think about things. Now, I don't know who of you were in the keynote this morning, and the speaker was saying that an important thing to do is just to start somewhere, like if you've got a problem to solve, just to start. Now, if you ask me, when would I use a Kotlin notebook? That would be a perfect time for me to pick a Kotlin notebook. If I don't know the problem yet, I don't know the solution, I don't know the API, I don't know the shape of the data, I don't actually even know what I want yet, then a Kotlin notebook is like a scratch file, which I can just open in my IDE, and I can just start typing something. I can think I need an API that looks like this. It needs to be canvas, and then I just want to be able to draw a line on a canvas, and then I can start writing the API like that, and then I can evolve and iterate and create those functions. The other time I would use a Kotlin notebook is if I want to show you something, or if I want to show anybody something, because it's so powerful to be able to have the code and the output right next to each other. And changing the code here, let's make this 20, run it again, and it should be shorter. So to be able to show how the code changes and have the output right next to it is super important. The other thing is maybe I'm exploring something and I want to write some notes along the way, or I have some links of things that I researched, the Lindenmayer systems, or all of the things I researched. I can just add it as markdown in this file. And this becomes like an artifact that I can use for teaching, for showing people things, and for recording my process. There are, however, some things that I didn't like so much about the notebooks. So these notebooks are JSON files underneath, and it's a standard format. It looks like it's a Python file, but it's not. It's just JSON. And what it does is this image, which is a new image that it created, it stores that image inside the notebook. So if I commit this notebook up into GitHub, every single time I run it and it makes new outputs, it's like it changes the file. I might not have changed the code, but it changes the file. So I didn't like that so much. So what happened because of that was, I found there were pieces of the code that I was creating while I was looking at these notebooks that kind of became firmer, that kind of settled into a shape. Like the tortoise algorithm became a tortoise, and then what happened is I moved that code out into a Kotlin file, because these notebooks can live right next to the Kotlin files in your projects. So the canvas algorithm, the tortoise algorithm, the squirrel algorithm, they all moved into Kotlin files, and those files can be checked into source code control. The other benefit of that is that if you're in a notebook and those things don't change, these cells, if you run them out of sequence, they just build like a worldview of what they know about in each of the cells. But if you pull in code from your projects, then you can have a set number of functions that you know you've got available for you to use. And you don't need to rerun cells earlier in the notebooks to get things to work. Okay, so that was my contemplation. And so what I found was I really liked it, but it also changed my process. It changed the way I was approaching problem solving. It made me think about what I want first and then figure out how I was going to do it. It made me just try things and just play around. And that sense of fun and wonder was very refreshing. Okay, so what's next? This is about the end of my talk. There's a GitHub repo with this. I'm just going to quickly flick across and show you the GitHub repo. Now, the cool thing about these Kotlin notebooks are that if they're small enough, you can read them. You can read them in the GitHub repo. The pieces are there. This is a different version, a different run, but you can read it like this, and GitHub can actually render this, because this output is, in fact, embedded inside the notebook. So it means it's quite accessible. So what's next would be, like, if you're curious about this, but you're not quite ready to jump in and code in it, you can just go and read what I've done in the Kotlin notebook. Also, there are a ton of links for you. You'll find them in that same notebook. There's stuff about fractals, so you can read up some more about fractals or Lsystems. You can play with them, and there's information about the data frames and the Kotlin notebooks in there. Or the other possibility is that you've been sitting for too long and you've been typing for too long, and then what you actually need is a walk in a real forest among real trees and a breath of fresh air. And with that, that's the end of my talk, except I need to do this.